Alright, so Chapter 8 Prep Quiz. The first 23 questions, they're really designed to help you out conceptually with what's going on here. And I'm not going to do video solution on them. But if you look at the right answers in, the graded tab, when you unlock this workbook, and you think about them, it should make sense. If it doesn't, shoot me an email. I'll explain it. If people don't understand, I can always, go back and make a video later. So, we will move down to the first computational problem. And make sure you do the first 23 before doing this. A sample of n cereal boxes. They have a mean weight. Construct a 95% confidence interval that the mean weight of all cereal boxes with the given information, and assume that the standard deviation of the population, sigma, is known. So the first thing you do in this case is you want to go to your equation sheet, which is posted now onto Canvas, and you want to find an equation for confidence interval. This is Chapter 8 material. So interval estimation of x bar when your standard deviation of the population is known right here. Here is your confidence interval. So this is the equation we want to use. Let's see if we can copy that into Excel. I'm not sure if that'll work or not. Let's try it. Alright, so semi does work. Not wonderfully, but wonderfully enough to look at it. So here's the equation that we want to use. And it, this confidence interval is composed as two parts. Your point estimator, which in this case, since we're estimating the population mean, the point estimator is the sample mean. And then you have your margin of error term, which is E right here. And in this equation, the margin of error, you use the Z distribution, and that's because the population standard deviation is known. And, this is just the equation. So this is Z times standard deviation divided by square root of n, which little n is the sample size. That is your margin of error right here. So this equation and this equation are the same. The only difference is you see your E in this equation, what it is computationally. So the first thing we have to do is determine what x bar is, and I give it to you right here. I says there's a sample of n cereal boxes that yield a mean weight of 1.02. So 1.02 is our sample mean. Now we have to determine the margin of error. So let's set this up. We have E, and then E is composed of our Z term, our sigma term, so I'll put sigma in here, insert symbol, sigma, and n, or the square root of n, which I'll just put for e's, n to the 1/2 power. So, alright, we want a 95 confidence level. So if we're interested in the 95% confidence level, that means our alpha, which I might as well just insert the symbol. Once you use them, it goes down to this recently used symbol, so it becomes a lot easier than searching for it. So alpha, in this case, when you have a 95% confidence level, equals 0.05. We want to look at a Z term that has alpha over 2 over it, so our alpha over 2 value that equals 0.05 divided by 2, 0.025. So to determine what our z value is, that is z sub, alpha over 2, or z of 0.025, or we can just look into our standard normal table, which I don't have open for us right here. And we can find 0.025, this probability, in our standard normal table. So where is that 0.025? Right here. So that is, in this case, it's negative 1.96. So, you don't need the positive or negative. Since you're plussing or minusing anyways, it's like, multiplying by a factor of positive 1 or multiplying by a factor of negative 1, so it doesn't matter. Z, when you see a notation of z to, the 0.025, that represents the positive value of z, so that would be the positive 1.96. Whereas if you see like a negative z to the 0.025, where this guy is a subscript, that's going to be negative equals -1 times this. And let's just make this prettier. So that's what's going on there, but all you really have to know is that your z factor is 1.96. So let's construct, and make sure you do use the positive one, because if you use the negative one, your answer will be marked wrong in this. So just for clarification. So we know what our z value is. That's 1.96. Our sigma, that's given to us, 0.03. And now we just need the square root of n right here, or n to the 1/2 power. So square root of n, there we go, that's 5. Now we can figure out what our margin of error is. It is equal to this right here. You have to know that. You have to know that E equals this part of the equation. And so it just equals our z term times this, the population standard deviation divided by the square root of n. There's our error term right there. And so our error term is equal to this. Now we get the confidence interval. This pops up, and I've designed this box. It'll pop up once you fill in both these two boxes, then you get your confidence interval, and this is the correct answer. But the way my grading style works in Excel is it'd be kind of difficult for me to grade you if I had you type this in and account for like rounding error and stuff like that, which my quizzes currently still do. So I have this pop up, and you should be able to write it like this, but I'm making the assumption that if you can get your x bar and if you can get your e, then you can also write it like this too. So next question, what is the lower bound of the 95% confidence interval? Well, here's our confidence interval. It's 1.02 plus or minus 0.01176. The lower bound of that is 1.02 minus 0.01176, and the upper bound is 1.02 plus 0.01176. So let's just write lower bound right here, and this is equal to x bar minus our margin of error, and our upper bound is going to be equal to x bar plus our margin of error. That's that simple. So there's our lower and upper bound, and I will correct this while I'm at it. Obviously that will be there for you, so you wouldn't change anything right here. Next question. Well, I have these true and false already filled out for you, but next computational question. Alright, second computational problem. This is virtually identical to the first problem, but in this case the population standard deviation is unknown, and instead of me giving you the population standard deviation, I give you the sample standard deviation. And as soon as you realize that the population standard deviation is unknown, then you remember in that case we don't use the z distribution, but we use the t distribution. The t distribution is what you use when you don't know the standard deviation of the population. So go to your equation sheet, and we want an interval estimation using x bar, but in this case the population standard deviation is unknown. So here's our equation for the confidence interval. Let's copy that, and we will paste it in here for our viewing pleasure. Great. Just put that right here. So, and the same thing's going on here. Your confidence interval, since we are still doing a confidence interval of the population mean, the point estimator is still the same. The point estimator is x bar, and the sample mean. Same on both sides. And then your margin of error now is different. And the difference now is that you use the t distribution instead of the z, and we're using the sample standard deviation, not the population standard deviation. So only difference is we're going to repeat the same process as before. So x bar is given to you. It's 1.02, so that's pretty easy. The margin of error, let's make, we have e, and e is composed of our t variable, our s, sample standard deviation, and n, the square root of n, which is the same as n to the 1/2 power. So let's fill in what we know first, and then we'll work on the harder stuff. Our sample standard deviation is given to us as 0.03. N to the 1/2 power is the square root of n, which is given to us, and now we just have to determine what t is. T is the when determining t, the first thing we need to determine is what our confidence level is, and our confidence interval is 95%. So 95% confidence interval. Now in this equation, and I'm going to zoom in because this is important, you see this t variable, and in this equation what's used as the subset to t is alpha divided by 2. That represents the area in the upper tail, such as this section right here, such as section R. Okay, so it represents the area in R, but different books have different notations for this subset, and we use, or this equation uses alpha over 2 because I think that makes the most sense. Alpha is the amount of air that's acceptable, which is 0.05. The area in the right-hand tail is 0.05 divided by 2, so 0.025. But your book uses the area of the right tail. They use the notation of alpha for that, not alpha divided by 2. I think that's confusing. Different tables, different books are going to use different notation for this. So you want to think about it in terms of area of upper tail. Okay, and remember, whether it's a Z table or a T table, they both have the bell shape. They're both symmetrical, so your area of your upper tail is the same as the area of your lower tail. And what we want to, the area of the upper tail is equal to area of one of the tails. So this language is important when we look at our T table, which you'll see in a little bit. Anyways, our alpha divided by 2, or the area in one of their tails, is equal to 0.05 divided by 2, which is 0.025. And the next thing you need to know for a T table is the degrees of freedom. And we always need to remember that this will not be given to you. You always need to remember that the degrees of freedom is equal to n, which is the number in your sample, minus 1. Got it? Memorize it. So that's really not a hard formula to memorize. It's n minus 1. So that is equal to 25 minus 1. So we are interested in a T table with the or a T value when the area in the upper tail is 0.025 and the degrees of freedom is 24. And we want to go to our T table, and this is the way the T table works. You have degrees of freedom going down here. This subset represents the cumulative probability, so don't focus on that as much as you want to focus as the one tail right here. This means the area in one of the tails. So the area in the upper tail or the area in the lower tail. In this case, we want to use 0.025. That's right here. So we want to use this column. And right here, this shows the area of two tails. That's our alpha. Our alpha is 0.05 because that's like our total amount of air that we are allowing, and both of those, that air is in both the tails. So two tails has 0.05, one tail has 0.025. Either way you look at it, you get to this column. The 0.975 comes into, that's your cumulative probability. That comes into saying, let me go back to this sheet. The area in our upper tail in this example is 0.025, and the cumulative probability is everything to less than or equal to that, or everything left of that value. And I know this says Z, but you could replace this with a T and it'd be exactly the same. So all the area to the left of that is your 0.975. So that's how they're looking at that top column. Anyways, getting distracted. Area in one of the tails is 0.025. Degrees of freedom is 19. So we look at that value right here. And our T value is 2.093. Let's go back to Excel. Zoom out a little bit. And honestly, we should keep these small. So our T variable is 2.093, and I want to make that small. And now we can determine what our margin of error is. It is the T times the sample standard deviation divided by the square root of our sample size. So t multiplied by the sample standard deviation divided by the square root of n. And there's our error term. So let's put that in there. And once again we get our confidence level popped in. Now if you were answering this question by hand, this is exactly what you'd write right here. So I'm hoping you can bridge the gap between right here and right here. Not too difficult. And once again we have lower bound and upper bound. This is the same story as before. The lower bound is simply the point estimator minus the margin of error, and the upper bound is equal to the point estimator plus the margin of error. So now the second way you could write a confidence interval, just for your own knowledge, would be the lower bound, so 1.007 comma upper bound 1.03 and then 3 rounded. So this is your second way to write a confidence interval. Pretty easy. And I'll fix these again. Alright, so proportion question for confidence interval. 95% confidence interval. There is little n, 100 students in our survey, and 90 answer yes. What is the confidence interval of the population proportion? So, exact same process as before. We say, oh, we're working with a proportion. Let's look at what confidence interval we have for a proportion. Oh, it's right here. So let's copy that in. Didn't work. Not working anymore. There we go. I'll put that over here. So it's the same thing. Now we're looking for, we're interested in the parameter of interest is the proportion of the population, which would be represented by maybe little p or maybe big P, just depending on the notation. But the point estimate of that is little p bar, which is the sample proportion, and our margin of error, which is E, is this term right here, which we found from our equation sheet. So and this is also on the equation sheet, but maybe it's obvious. Your proportion is going to be the number that say yes to whatever you're looking at, or the number that are in your proportion compared to the total number in your sample, or for your population to be the total number that agree to the proportion compared to the total number in your population. So our proportion is just going to be equal to 90 divided by 100, 0.9. Now we have to find our margin of error. So to find our margin of error, we'll make that an E right here. We need to know our Z term, and we need our P term, and I should say P bar, and we need our N term. And then that's going to help us find our P bar. This is our P bar and our 1 minus P bar term, and then N will be the same. and then I'll just put this I'll just use a variable t for like the total under the square root, which is just your p bar times 1 minus p bar divided by m. We'll just put that to the 1/2 power. And this is just notation I'm using. You can use whatever notation you want, but ultimately you just have to do this calculation. And I'm going to move actually all these things down one, because we need the z for that too. So yeah, this is kind of like duplicate partially of what's going on right here, but you know, in order to get that total t value, and this is our quantity under the square root. Alright, so now we know what's going on. Our z term, well, we have to figure out what alpha over 2 is. We have a 95% confidence interval. So our alpha is 0.05. So our alpha over 2, or our area in the upper tail, or area in one of the tails, is, I'll just write alpha over 2. 0.05 divided by 2, 0.025. And, you know, we can look in our z table and find, you know, the 0.025 in this z table and find the z value. We've already done this 100 times though for a confidence interval of 0.95. Our z value is 1.64, and you can look that up in the z table and confirm it. So our z value is known, and our p bar value is known, and our n value, number in our sample, is known. So now we can just start to plug this stuff in, and we will repeat z, and we'll repeat the p bar. Our 1 minus p bar equals 1 minus p bar. Our n, we will repeat that, and our t, which I use t to represent everything under here. So that's going to be equal to p bar multiplied by the 1 minus p bar divided by m. Now we have to take that entire quantity and take that to the 1/2 power. There's our total value under, this is, you know, the whole square root term, and our error term is going to be equal to our z value right here multiplied by that square root term. Let's double check. Yep, and our t term does not include the z. There we go. So now we can determine what our confidence interval is. You know, it's just this p plus or minus this error term. There it is, so beautiful. And once again, the upper bound will be our point estimator plus the margin of error, you know, 0.9 plus 0.0492, and our lower bound will be 0.9 minus 0.0492. So, and once again, I'll fix these. Great. Last question. Damn, I thought this was going to be hard. Anyways, so this is a question where you're finding how many little n, the number that is appropriate for you to use in a sample size, and we want a confidence interval, 95% confidence interval, and we want, you know, it's going to tell you what your margin of, what you want your margin of error to be. We want our margin of error to be 0.05 labels, and we're going to assume that our population standard deviation is going to be equal to 0.03. So we need to find an equation that is going to solve n for us, and we can look in our equation sheet, and we're not using a proportion, so we wouldn't want to use that. And so we either want to use this guy or we'd want to use this guy. But I tell you to assume sigma. Assume this population standard deviation. So in this case, we're not assuming, you know, the sample standard deviation. We're assuming the population standard deviation. So we want to use the one where we believe the population standard deviation is known. So this is our equation. This is our guy. Let's put him in here. That's not it. Back here. There we go. So we got to find our z term once again, and our z term alpha over 2. Alpha is 0.05. Alpha over 2 is the area in one of the tails, 0.025. So you could look up that in the table, find your 0.025 in the table, or you can realize, since we're dealing with a two-tail problem, which everything in this chapter is a two-tail problem, and if we're dealing with a 95% confidence interval, and this won't, don't just memorize the 1.64 for this confidence interval. You got to be able to look up in the table in the quiz or the test or the exam or whatever. It's not always going to be 95%. You need to realize, you need to be able to look it up. But anyways, long story short, alpha equals 0.05. Alpha over 2 equals 0.025. Look up the when is the what is the z-score when the probability of z being less than that z-score is equal to 0.025. It's 1.64 or negative 1.64. But we want our z term to be positive, so we use the positive 1.64. And in this case, it doesn't matter because you're squaring the z term anyway. So if you square 1.64 or if you square negative 1.64, you're going to get the same answer either way. So, don't get confused with that. It doesn't really matter in this case. Anyways, our sigma, I'll paste some values right here so I don't have to look up the symbol. Our sigma is, whoa, that is definitely, okay. I did not fix these, but we'll fix them now. We have a sigma of 0.03, and we want our error margin to be 0.05. So sigma equals 0.03, and our error margin equals 0.05, and so we can find e squared. And now we can solve this problem. Well, let's do sigma squared too. F2 will go into this automatically, so you don't have to click it. Keyboard shortcut. So, and let's just do z squared too while we're at it. Jeez. So now we have all of our terms squared, and we can figure out what n equals. It is simply equal to z squared times the standard deviation of the population squared divided by e squared. And then we get our n value. This is obviously not a really good problem, so I am going to change this Bear with me. Let's say we change this to .005. Oh, beautiful. Now that's exactly what we want. Alright, so process is the same. I'm not going to read this video. Anyways, we get our n to be 96.8256 now. That means for, this given population standard deviation, and for this given, I have to expand this out, for this given margin of error, we need at least 96.8. So whatever this n is you solve for, you always round up. Always round up. In this case, it'd be 97. So we need at least 97. But this was a 96.2. You still round up to 97. So you can't have 96.8 people. And, when you solve for this n, it basically says you need at least whatever n you solve for. And since you can't have like a point of a person, that's why you always round up. So 97, and I'll do round up. Yep, number of digits, 0. Boom. That's it. Easy peasy. And, I did these problems, and, these problems in there. They're really easy. They follow each other one after the other. It took me literally about 10 minutes to do it. So, even though there's 45 questions, it's really not that bad of a quiz. Thanks. See ya.